In this video, we're going to look at one of the more important applications of infinite series, which is a geometric series. An infinite geometric series has the pattern summation n goes from 1 to infinity a times r to the n minus 1. This is equal to a plus ar plus ar squared. So we're plugging in different numbers for n. For example, n equals 1 gives us 1 minus 1 is 0 in the exponent. So we get a times r to the 0. R to the 0 is 1, so the first term is a. For the second term, plug in n equals 2. 2 minus 1 is 1 in the exponent, so we get a times r. And similarly, we get ar squared plus dot 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 and ar to the n minus 1 as a general term, and so on. And of course, a, which is the first term, is not 0. Now let's consider the nth partial sum, Sn, is equal to k goes from 0 to n minus 1, a times r to the k. And let's expand out this series, so we get Sn is equal to k goes from 0 to n minus 1, a times r to the k. This is equal to a plus ar plus ar squared plus ar to the n minus 1 as the last term, because this is the nth partial sum. Now, multiply both sides by the common ratio r. So we get rsn is equal to ar plus ar squared plus ar cubed plus ar to the n. So multiply both sides by r. Now subtract rsn from sn, and we get sn minus r times sn is equal to, if we subtract these, we get ar cancels with ar squared minus ar squared is 0, and all that's left with is the first term of Sn and the last term of Rsn, which is this one, ar to the n. So we get a minus ar to the n. Now factor out Sn from left-hand side, so we get Sn times 1 minus r is equal to a minus ar to the n, and we have Sn minus r times Sn is equal to a minus ar to the n. Let's assume that the common ratio r is not equal to 1 and a is not equal to 0. So we factored out Sn. Sn times 1 minus r is equal to a minus ar to the n. Now divide by 1 minus r to isolate Sn to solve for the nth partial sum. We get Sn is equal to a minus ar to the n divided by 1 minus r. We're going to use this partial sum Sn to analyze the values of r, the values of the common ratio for which the infinite geometric series converges and diverges. So let's first consider absolute value of r less than 1, or equivalently, r is between 1 and negative 1. Clearly, we know that the limit as n goes to infinity of r to the n will be 0 if r is a fraction between 1 and negative 1, and a fraction raised to a high power, a fraction that's less than 1 in magnitude, raised to infinity will of course approach 0. So the limit of Sn as n goes to infinity is equal to limit n goes to infinity a times 1 minus r to the n divided by 1 minus r. Let's factor out a over 1 minus r times the limit n goes to infinity of 1 minus r to the n. Now, we showed that r to the n is going to approach 0 as n goes to infinity, so the result is going to be the limit as n goes to infinity of Sn is equal to a over 1 minus r. So the infinite geometric series converges in the case when r is between 1 and -1, and this is of course the sum of the geometric series. Now let's consider r equals 1. Let me underline these. So r equals 1, we get Sn, the nth partial sum, which is a plus ar plus ar squared plus all the way to ar to the n minus 1. Well, this is going to be, because the common ratio is just 1, so we get a plus ar, which is just a plus a. And the very last term, of course, is also a. And there's going to be n of these. So the result is na. So the limit as n goes to infinity of Sn is going to be limit as n goes to infinity of n times a, and this is of course going to go to plus or minus infinity depending on the sign of a. Now let's consider the case r equals -1. So the nth partial sum, Sn, is equal to a plus ar plus ar squared plus dot 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 ar to the n minus 1 is equal to, we get a plus a times -1 minus a, and then ar squared will be -1 squared is plus 1. So anytime the common ratio r is raised to an even power, we're going to get -1 raised to an even power, which is plus 1. And anytime the common ratio is raised to an odd power, -1, say, to the power of 3, it's going to give us -1. So we're going to get a minus a plus a minus a, and all the way to the last term, a times -1 to the n minus 1. So if you look at the partial sums, S1, which is just the first term, that gives us a. S2, the sum of the first two terms, which is a minus a, gives us 0. S3, the sum of the first three terms, which is a minus a, which is 0 plus a, that gives us a. S4 equals 0. So we see the pattern. The limit as n goes to infinity of Sn does not exist. Does not exist. Since Sn oscillates between 0 and a. So summation a times r, which is -1 to the k goes from 0 to infinity, diverges. This geometric series diverges when the common ratio r is equal to -1. Let's look at the case absolute value of r is larger than 1, which means, of course, the common ratio is larger than 1. For example, the common ratio is 4/3, that's bigger than 1, or the common ratio is less than -1. For example, r is equal to -4/3, its magnitude is less than 1, because absolute value of -4/3 is equal to 4/3, which is bigger than 1. So Sn is equal to k goes from 0 to n minus 1, ar to the k, diverges. Why does it diverge? Because the limit as n goes to infinity of r to the n does not exist in this case when the magnitude of the common ratio r is bigger than 1. Does not exist. That means the infinite geometric series will, of course, diverge. K goes from 0 to infinity, ar to the k diverges. Let's do a summary. So this is a summary of the things that we've talked about so far about the geometric series. Let a not be equal to 0 and r be real numbers. Then the series summation n goes from 1 to infinity, ar to the n minus 1 is equal to a plus ar squared all the way to ar to the n minus 1 plus the infinite number of other terms. This infinite series converges if the absolute value of r is less than 1, or equivalently, r is less than 1 and larger than negative 1. And its sum is given in closed form, so the summation n goes from 1 to infinity, ar to the n minus 1. We have a formula for the sum of this convergent geometric series to be equal to a divided by 1 minus r, and this happens when absolute value of r is less than 1, or equivalently, when r is between 1 and negative 1. Now, if the absolute value of r is larger or equal to 1, for example, if r is equal to 5 over 2, or r is equal to negative 5/3, the geometric series diverges. And we also looked at the case for finite n. For finite n, the sum will always converge because there's a finite number of terms, and you can always add up a finite number of terms and get a sum. So for finite n, we also have a closed formula. K goes from 1 to n, a times r to the k minus 1 is equal to a times 1 minus r to the n divided by 1 minus r, provided the common ratio r is not equal to 1. All right, let's look at some applications. So here we have find the sum of the following geometric series if they exist. For the first case, we have 1 minus 4/3 plus 16 over 9 minus 64 over 27 plus minus dot 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 minus 4/3 to the power of k minus 1. For the second case, we have 1,000 as a first term, 500 as a second term, so 1,000 plus 500, it seems to be halving every time, plus 250 plus 1,000 times 1/2 to the k minus 1. And our goal is to find out whether they converge, and if they converge, to find the sum. So for part A, we have summation. K goes from 1 to infinity minus 4/3 to the power of k minus 1. Now, in this case, we're given the general term, and that kind of helps us out. But you may not be given this general term, and you have to figure out the pattern on your own. It's not too hard to do, because we can see the first term is 1. That's our a here. That's like 1. And the common ratio is r. Why is it r? Because you can always take this term and divided by this term, we get negative 4/3 as your r. Or the ratio of any two successive terms. You can also take 16 divided by 9, divided by negative 4/3, and you get negative 4/3. So we have this geometric sum, and our goal is to find out, does it converge or does it diverge? Well, this one is going to be easy. It diverges. Why does it diverge? This infinite geometric series does not have a sum. It diverges because the common ratio r is equal to negative 4/3, which is less than negative 1, or equivalently, absolute value of r is larger than 1. Now on to the second example. So we have summation. K goes from 1 to infinity. The first term is 1,000. The common ratio is 1/2 times 1/2 to the power of k minus 1. This infinite geometric series converges. It has a convergent sum. The reason it converges is because the common ratio, r, is equal to 1/2, is less than 1, or absolute value of r is less than 1. So the absolute value of the common ratio is less than 1. This infinite geometric series converges. It has a sum. We need to find that sum. So we have summation. K goes from 1 to 1,000. 1,000 times 1/2 to the k minus 1. And we have a formula for a convergent geometric series if the absolute value of r is less than 1. Summation a r to the n minus 1. N goes from 1 to infinity. This infinite geometric series converges to the sum a over 1 minus r if absolute value of r is less than 1, or equivalently, r is less than 1, larger than negative 1. And that's the case here because we have r equals 1/2. The first term is 1,000. Now, it's always important to verify the first term. Just plug in k equals 1, we get 1 half to the power of 1 minus 1, which is 0. 1 half to the 0 is 1 times 1,000. The reason it's good to verify this is if this index started at different numbers, say it started at, for example, 2 or 3, then this 1,000 would not necessarily be the first term. So to be on the safe side, plug in your starting index, in this case k equals 1, and plug it into the expression for the general term, and make sure that you have the right number for the first term, which is a. So a equals 1,000 is the first term. And the common ratio, r, is equal to 1 half. This is the common ratio of the geometric series. Common ratio. And since r equals 1 half is less than 1, so we have the common ratio is 1 half, is less than 1, so we have a sum for this series. This series converges to a sum. S is equal to a divided by 1 minus r. This is equal to a is 1,000. A is equal to 1,000 divided by 1 minus r, which is 1 half, and we get 1,000 divided by 1 half, and the result is 2,000. And this geometric series, this infinite geometric series, converges to a finite sum, which is 2,000. So let's summarize. We have 1,000. This is the expanded form of the geometric series, plus 500, plus 250, and the general term is 1,000 times 1 half to the power of k minus 1. This infinite geometric series converges to 2,000. In compact form, we can write this as summation k goes from 1 to infinity, 1,000 times 1 half to the power of k minus 1. This infinite geometric series converges to a sum, converges to S, is equal to 2,000. All right, thanks.